name is Christian Holz. We have 4 talks today, and Daniel's going to start with the first talk on the personalized compass, a compact visualization for direction and location.
All right. Thanks, Christian, for the introduction. Good morning, everyone. My name is Daniel Miau. This is joint work with my advisor, Steve Feiner. Today, I'll be talking about a navigational instrument called personalized compass, which extends the idea of a conventional compass to address the where's X problem. I'll just jump in to give you an example of the where's X problem. If you type in the search keyword, first national park in the world, this is the search result you will see. But the small map here shows the details, but lacks context. To access the context of the map, you have to switch to a different map application, then repetitively zoom out. At the overview level, however, details are lost, not to mention the search engine context. We refer to this type of problem as the where is X problem. Since in many situations like this, we found ourselves scratching our head and asking the question, where's X? This problem is the result of a condition called desert fog in literature, which states that when the information space is devoid of meaningful cues, it becomes difficult or impossible for users to make any decisions. This where is X problem is everywhere. It can be found in many applications related to our daily lives, or on maps of all sizes, even when there's no map, such as the case when one tries to figure out where this photo was taken from the geotag in Instagram. Now, a lot of times, we only want to get a rough sense of where X is. To be more specific, let's say where X is in relation to some reference frame that we know. So in those situations, we are wondering, do we need all the context switches and interactions to access all the data? We proposed a lightweight navigational instrument called personalized compass, or P-compass, to address this issue. To explain the idea, let me start with the compass we are all familiar with. So a compass indicates the direction of north, but I guess it's not very helpful in this case. If we add needles to indicate the directions of several major U.S. cities with respect to the reference point, which is Yellowstone National Park in this case, we know Yellowstone is somewhere in between these 3 cities. This seems to be promising. If we scale the needle such that the length of each needle indicates the distance to each city, now this compass, a P-compass, essentially uses landmark POIs to help users establish a reference frame. In doing so, P-compass provides an approximate answer to the where is X question. P-compass is compact, can be integrated into a map, or as a standalone location indicator. P-compass can be integrated into a visual content, so to provide context of this image of Yellowstone National Park, or embedded into interactive visual content, such as Google Street View. In some extreme cases, P-compass might be embedded into textual content, such as the example we show you the last page in our paper. Let me quickly show you P-compass in action. P-compass is a compass. It occupies a small footprint. For the purpose of explanation, we can make the P-compass bigger. Here, the 3 cities provide the context of this otherwise confusing map. As the user zooms out the map, a field of view box indicates the location of the 3 cities with respect to the boundary of the display. And in our implementation, when a POI becomes visible, its needle disappears. Using simple gesture, user can resize and translate a P-compass. This where is X problem is closely related to the overview plus detail problem in literature. As suggested by Corbin et al., there are 4 techniques to communicate overview and details. Zooming interface separates overview and detail temporally. Spatial separation arranges overview and detail side by side. And focus context aims to blend the scene between overview and detail. Cube-based technique uses proxy to indicate important off-screen objects. Here, by completing the shape of those partially included triangles called wedges, user can estimate the location of off-screen objects. We observe that P-compass is a hybrid technique. P-compass is similar to a simplified version of the overview map, but superimposed on the detail map. At the same time, P-compass uses proxy to indicate the important off-screen objects. We prototyped P-compass and the Wedge on a custom map application, which supports standard map interactions such as pan, zoom, rotate, as well as the location search. We manually enter a list of POIs as the location database and apply a simple algorithm to select up to 4 POIs to form a balanced compass. In other words, POIs roughly spread out in all directions. I use this app regularly for iterative prototyping and field testing for a period of 1 year, specifically in New York City and London. So intuitively, the idea of using landmark POIs to help users establish a reference frame is general. So an off-screen visualization technique, such as Wedge, should be as effective as P-Compass. We're interested in knowing if that is the case, and we made 2 observations. Our first observation is on characteristics. Recall that Wedge guides users to place a POI at the display edge using the idea of shape completion. Here, United Nations is located at the apex of the completed triangle. However, Wedge also requires users to estimate the location of those POIs before those POIs can be used to support decision making. For example, one must first estimate the location of the United Nations and the Empire State Building before one can decide which one is closer and by how much. For P-Compass, here's a close-up. It's easy to see the relationship between off-screen POIs, but it's difficult to place those POIs at the display edge because one will first need to perform the estimation using the field of view box, then scale the estimation to match the physical size of the display. Our second observation is on scalability, which means how the distance of an off-screen POIs affect the performance of a visualization technique. Scalability is important because not POIs are close to the display edge in real life, and with sufficient zoom, any close POI can become distant. In this example, both United Nations and the Empire State Building are further away from the display edge. It becomes challenging to locate the 2 using shape completion, especially for Empire State Building. Therefore, it is also much difficult to infer the relationship information between the 2. Scalability can mean the size of display too. A small display further presses the wedge legs to be almost parallel, which further reduces the effectiveness of wedge. In comparison, P-Compass communicates relationships, and relationships stay constant regardless of the distance of the size of the display or the scale of the information space. To recap, we made 2 observations. Our first observation is on characteristics. We found that 2 techniques are complementary. Wedge's strength is to place a POI at the display edge, while P-Compass' strength is to communicate relationships. However, on scalability, as the distance of the POI increases or the size of the display decreases, one should choose P-Compass over Wedge. Based on our field experience, we designed a laboratory user study to compare P-Compass and Wedge. The study includes 5 tasks which are inspired by common activity in the city life, such as estimating the locations, distance, direction over subway station, or using landmarks to help user interpolate or extrapolate an unknown location. In the interest of time, I would cover 2 of the tasks in this talk. Locate is adapted from the existing study. And to match the setting in the existing study, this task was performed using an emulated smartphone on a desktop monitor. In this task, the participant sees a wireframe indicating the boundary of a smartphone display. And the participant also sees a visualization indicating the location of the off-screen subway station. The participant's task is to estimate the location of the subway station and to mark the answer with a mouse cursor. Let me show you the close-up of these 2 visualization conditions. Wedge is on the left and P-Compass is on the right. We vary the distance of the off-screen subway station from 5 centimeters to 30 centimeters. For localized, the participants view the visualization on a smartwatch, emulated on a smartphone, and input the answer to a nearby computer. On the smartwatch display, the participants see the visualization showing the relationship between 2 off-screen locations, a hotel and a train station, with respect to the display centroid, which indicates the participant's location. The participant's task is to estimate where she is with respect to the hotel and the train station on a desktop monitor. We made two hypotheses for these two tasks. For locate, we hypothesized that Wedge will yield more accurate result for close POIs. For P-compass will yield more accurate result for distant POIs. This interesting reversal is because shape completion works well when the POI is close to the display edge, but quickly becomes error-prone as the distance of POI increases. And for localized, we hypothesized that P-compass will yield more accurate result because P-compass communicate relationships. We recruited 26 participants from the general population of the university. 13 of them were female. I'll quickly highlight the results of these two tasks. Here are the results for locate. I'll comment on errors first. Lower is better. The blue bars corresponds to P-compass, and the yellow bars corresponds to Wedge. You can see that Wedge was more accurate for close POIs, and P-compass was more accurate for distant POIs. We tested the errors of these two extremes and found significant difference. In terms of completion time, it took longer for P-compass to complete the task. This matches our earlier observation that P-compass requires more mental effort to place the POI at its absolute location. For localized, in terms of errors, lower is better. We found P-compass is significantly more accurate than Wedge, and there's no significant difference in terms of completion time. So the two hypotheses are therefore supported. Like many techniques, P-compass has its own limitations. First, P-compass requires personal a priori knowledge of a space. The more detailed knowledge a person has, the tighter reference frame a P-compass can provide. And our prototype currently uses a list of manually entered POIs as the location database. In a way, the prototype is only personalized to myself. But there are data mining and the learning methods to collect and update a set of POIs that may be known to a given user. Last but not the least, we apply a simple algorithm to select POIs from the list. But we noticed that the distribution of POIs and the distance ratio of POIs could all affect the accuracy of summation. So the investigation and development of a POI selection algorithm could be interesting future work. In this work, we propose a navigation instrument called personalized compass, which extends the concept of a conventional compass. In a nutshell, P-compass communicates not only the direction of north, but also helps users establish a reference frame. In doing so, P-compass provides an proximity answer to the where is X question. We designed and ran a user study to compare P-compass and Wedge. Our results suggest that the two techniques are complementary. However, as the distance of the POI increases or the size of display decreases, one should choose P-compass over Wedge. So, while working on this project, we realized that there's one interesting idea, interesting question we don't quite know how to answer. So I'll end the talk with this question. In cognitive psychology and urban planning, it is known that there are separate entities play important roles in humans' mental maps. And P-compass currently takes advantage of landmarks only. By strategically using those building blocks of the mental map, it's possible to create a space piece, a navigational instrument that can answer where X is with a single glance, much similar to how a timepiece can answer what time it is with a single glance. I think this is an interesting question to think about. We'd like to acknowledge NSF for the support, and thanks for all the people who have helped in this project. And finally, we'll be doing one last demo immediately after this session, so please come to our booth, number 1, if you're interested. Thanks for your attention. I'll be happy to take questions.
Okay, so questions welcome. We have one microphone right here.
Hi, Daniel Ashbrook from the Rochester Institute of Technology. I'm curious if you've thought about ways to add things other than distance to the visualization, other than spatial distance. For example, the amount of time it might take to get somewhere, or are there mountains in between me and this point of interest, or other features aside from just pure as the crow flies distance?
Yeah, yes, certainly we think about that. I think especially like here in the Bay Area, from here go to Berkeley, you have to go indirectly. But adding those information might confuses people because then the length of the needle does not convey the actual distance. So I don't have a very good solution to that, but I think that certainly is an interesting future direction. Yeah.
Thanks.
Yeah. Thank you.
I'm really hoping you have backup slides because I was really curious about the distance. And I understand you didn't have time to talk about this, but maybe you have a couple of minutes now because I know, like from reading the Halo and the Wedge papers, that the participants in their studies overcompensated and underestimated the distance, right? And I was wondering if you saw something similar, in your study when you compared the two, as well as for your visualization.
So you mean for the locate task, right?
Yeah.
To estimate distance. Yeah, certainly I noticed the same thing for Wedge. People actually usually underestimate. And it seems to me that for P-compass, people actually tend to overestimate. Yeah.
Okay. Okay, cool. And the second thing I was curious about is, we all love maps. That's cool, and it's a great, obviously, example and thing to start with. I was wondering if you'd ever thought about like generalizing this. Does this work for other kinds of navigations, like not geospatial data, but other kind of
yeah, so we're thinking so this is a general navigational instrument, so I think can be applied to other spatial domains such as scientific visualization, or right now I only apply this to a 2D space, but I think can be extended to 3D space as well. Or for example, like navigating within the human body, so all the organs are in different locations. I think that might be a possibility. Yeah.
Cool. Okay, let's thank the speaker again.